Hi everyone, welcome to this video. So now that we know, we've just learned about standard candles and we know that we're able to measure the distance to very, very far away objects. So what we can do from this, now that we know the distance to things and we can observe starlight and actually observe spectra for different stars at various distances, we can combine those two pieces of information and learn a lot about the way that the universe is structured. And astronomers have done this, and Edwin Hubble, who obviously the Hubble telescope is named for, he noticed something really cool.
Right. So as we said before, we really want to use positions and velocities together to map out the structure, the dynamics of the galaxy or the universe. Now that we have standard candles, we can measure the positions of different galaxies, how far away they are. And so Edwin Hubble was doing a survey of distant galaxies to measure how quickly they were moving towards or away from us. This is via the Doppler shift, which we discussed last week. So looking at the spectra of these galaxies and looking at all of their lines that you could detect in their spectra, which we know the intrinsic wavelengths of. And so he measured what wavelengths they were actually observed at, and then you can infer that they're moving towards or away from you at some velocity. And this was in the 1920s in California at Mount Wilson Observatory. And he found something a little shocking, which was that all of the galaxies were moving away from us. Nothing's really moving towards us, and the further away you are, the faster the galaxies are moving away from us. And so that's really weird. That implies one of two things: that maybe we're just at the very center of the galaxy, but that doesn't seem likely. So it must imply that just the universe is growing in some way, that space itself is expanding, and things effectively are getting stretched out. So when you're further away, there's more space between us, and so there's more stuff to stretch out, and so that stuff appears to be moving further away, or moving away faster, I should say. And so Hubble worked out what that means in terms of how quickly things are moving away from us. He got the number massively wrong. He was off by about a factor of 10, but he got the concept exactly right. This is something that we've named after him. We call it Hubble's law now, and he's very famous, became the Hubble Space Telescope and things like that. There's been a lot of controversy over the intervening 100 years in refining what the value of Hubble's constant is. There's still a debate about what it is, although we've gotten much, much more precise than we used to be. But right now the answer is something like 70 kilometers per second per megaparsec. So every megaparsec, which is 1,000,000 parsecs, 1,000 kiloparsecs, if your galaxy is 1 megaparsec away, it's moving away from us by about 70 kilometers per second. If it's 10 megaparsecs away, it's 700 kilometers per second.
Yeah, and you might think, oh, that's not a lot, 70 kilometers per second, when we were just talking about all the velocities of how fast things are moving, but we are talking about, I was about to say astronomical distances. We're talking about cosmological distances, very, very large distances. So this actually becomes extremely important when we're looking at things further and further away. And it's also worth noting that it appears, because of the way that the universe is expanding, it appears that things really far away from us are moving away faster. But if we were right next to that galaxy, it would still follow Hubble's law. It would be moving away at a rate that follows the 70 kilometers per second per megaparsec. So it's not dependent. What you observe is dependent upon where you are, but we are not at the center of the expansion is something that is worth noting. And we'll talk more about the universe and the expansion of the universe in time to come.
Yeah, that's a great point. And so as Kate said, the universe is really, really big. She didn't quite say that, but she implied that. And so we're talking 70 kilometers per second at 1 megaparsec, but when you go to many, many, many parsec away, or megaparsec, the galaxy is, use a technical term, enormous. And so
Ginormous.
It might even be ginormous, yeah. And so we can start talking about galaxies that are moving away at a significant fraction of the speed of light. And so we don't really talk about that in kilometers per second anymore. We start using a term called redshift.
And we touched on this in the early parts of the course when we were talking about how things are moving away from you, and we were talking about the Doppler effect and redshift and blue shift. When you get down to really, really far distances, nothing's actually moving towards you. It's moving away from you much faster than it's moving towards you. So yeah,
right. Yeah, so we just talked about a cosmological redshift as effectively a proxy for distance through Hubble's law. That something at a redshift of 1 means that it's moving away from you at roughly half the speed of light, and so then you can work out what the distance to that would be, and as long as the expansion of the universe is constant over these big timescales, you measure exactly what that distance is.
So we have an exercise for you, which is we want you to assume that Hubble's constant is constant, that it has not changed over the age of the universe. And what we're going to do is we're going to give you a few different values for Hubble's constant. And what we want you to do is work out the age of the universe using dimensional analysis, which Ben showed us how to do early on in the course. Using that, look at the units for Hubble's constant and try to work out what the age of the universe is with the different values that we give you.
Remember, those units that we give you are kilometers per second per megaparsec. And so it's interesting that kilometers is a distance, seconds is a time, of course, megaparsec is a distance. So there's some things that you could perhaps be clever with.
We leave that to you, and good luck, and we will see you in the next video.